Hi everyone, welcome to my lecture on calculus. It's an overview, which means I'm not going to go through all the detailed proof as in class. Instead, I will rephrase calculus to review the underlying framework and ideas, and to smooth the pathway to more advanced branches, such as abstract algebra, differential geometry, and functional analysis. Moreover, some numerical algorithms are introduced to show the connection with computer science, which is important in this era of AI. The first part is about the historical background of calculus, mainly about Newton, who invented calculus in the 17th century. In his famous second law of motion, F equals ma, the quantitative connection between interaction and motion are established. For Newton, his problem is about kinematics, which is how to measure the instantaneous velocity and acceleration of an object moving along given trajectory. Mathematics before calculus can only do with the simplest motion, thus uniform rectilinear motion, 匀数直线运动. In such a motion, velocity is a constant, both in direction and in magnitude. So one can substitute it by the average velocity v bar. But how to do with a long uniform motion? Newton introduced an ingenious concept called infinitesimal, 无穷小. Infinitesimal is smaller than any infinite quantity. And applied with knowledge of Euclidean geometry and elementary algebra, Newton can use infinitesimal to approximate curve by direct line and to extract the linear part of changes. And with infinitesimal in mind, an intuitive definition of velocity can be given as follows. When the elapsed time delta t approaches infinitesimal, the average velocity v bar will tend to the instantaneous velocity. Take a quadratic motion, for example. The average velocity v bar can be easily computed as at plus b and plus delta t. By dropping the infinitesimal delta t, we will get the instantaneous velocity vt equals at plus b. And using his infinitesimal version of calculus, Newton further successfully proved the inverse square law for universal gravitation, quite an astonishing result at his time. But in engineering and other subjects after Newton, the second law is applied in the other direction, which is from instantaneous causal interactions to prediction on long-term effect, done by integration of differential equations. When looking back to Newton's definition of velocity, you should notice the emphasized words approach and tend. This is just a process of narrowing down variation, and we call it the process of limiting, which will be elaborated in the following section. It was not until 19th century that a German mathematician Weierstrass laid down the strict definition of limiting using epsilon delta clause. By epsilon delta clause, the implicit layering down process in Newton's infinitesimal analysis is formalized into the controlled shrinking of target variables variation in response to the contracting of domain. A bit knowledge of cell theory and predicate logic is needed to translate the intuitive natural language into an ambiguous mathematical predicate, and vice versa. For example, Newton's definition about velocity is equivalent to C, that Vt is the limit of V bar when delta t approaches zero. And with the epsilon delta definition of limit in mind, it can also be written as for arbitrary epsilon bigger than zero, there exists a delta bigger than zero too, such that for arbitrary delta t, whose absolute value less than the delta, we have the absolute difference between Vt and V bar is less than epsilon. And here we have the most often used symbols and rules in three tables. Firstly, there are logical symbols such as for arbitrary, the exist, and, or, negation, implies. And for set operations, we have belongs to, subset, union, intersection, and complementary. And the last table is about negation rules for upon symbols, which is very important to prove with calculus by contradiction. And that's all you need to know about the mathematical logic to learn calculus. And I strongly suggest no further step into mathematical logic without guidance. And in the last page of this section, symbolized definition of limiting on functions and sequences are summarized, followed by their respective negation. The expressions are very clean and deduction friendly, you can see. And these formulas and their variants will be repeatedly used in probability theory. However, there is a loophole in this version of definition too. In next section, we'll show how to fix it using algebraic methods. In formal definition of limit, a well-chosen C is crucial for the proof of convergence, but how to know C in advance? In simple cases, you can just guess. And sometimes you can also get C by trick. Take a look at the example in the green box. The sequence is defined by the iterative equation xn plus 1 equals n plus 1 over xn. Assuming xn converges, we can replace x by c in the equation, like this. And so the quadratic equation for c, we get c equals the golden ratio. And we can use this result to check the convergence of xn. But most of the time, we just cannot find C with a simple algebraic form. Consider the Bessel series, which is the infinite sum of inverse of squares. Let Sn be its partial sum, which is the sum of the first n terms. Though the atom summation is simply 1 over n squared, it's impossible for normal people to foresee that C equals pi square over 6 and to check the convergence with it. Well, even C unknown, The sequence Sn has two distinct properties that strongly hinge convergence. First, it is monotonically increasing and bounded, which suggests that there must exist a least upper bound 最小上缺界 as a limit. And second, we can observe that Sn becomes tighter as n increases. And sequences likewise are called Cauchy sequences. And such probably suggesting a concentration point as the limit. And there is a special word for the existence of concentration point for Cauchy sequences called completeness, 完备性. Although intuitive sound, neither least upper bound nor completeness can be proved using elementary algebra. Indeed, we know nothing about real number in elementary algebra besides it's composed of rational numbers and irrational numbers. And to close, the loophole will lead to build our theory of real number first. And in the view of abstract algebra, R, the set of real numbers are not defined, but constructed from its subfield Q, the set of rational numbers, using the procedure called extension, 扩张. In the procedure, each element of the extended field is mapped to a subset of the original subfield, called its representation, 表示. The representation is deliberately constructed to support the desired property. Dedekin's card. For example, Dedekin's card is a representation of R to support the least upper bound, and the Cantor's Cauchy sequence is another representation to support completeness. It's proved that both representations are equivalent. So we have the following proposition for the constructed R. That is, R is ordered, complete, and with least upper bound. And moreover, R is Archimedean like Q, which says for arbitrary x, y bigger than 0 in R, there exists a positive integer n, such that n times x is bigger than y, and Q is a dense subset in R.